Right now, there is a star so enormous, it breaks every scale we have, so unimaginably large that if it somehow replaced our Sun, you would not be orbiting it. You would be inside it. Earth, Mars, even our giants Jupiter and Saturn would all be swallowed deep inside its atmosphere. Light itself takes 8 full hours just to travel around it. And the most extraordinary part, this giant has been silently sitting inside our own galaxy the entire time, hidden from us for decades. By the end, you will understand exactly how we found it, and why the laws of physics even allow something this massive to exist. And once you see its true scale, you will never be able to unsee it. Before we dive in, if you love exploring these kinds of deep space videos, a simple like or subscribe really helps this channel reach more curious minds like yours. Now, let everything soften, and together we drift into space. For centuries, astronomers believed they had a reasonable picture of what our galaxy contained. Not a complete picture, no serious scientist would have claimed that. But the broad structure seemed well understood. We had mapped thousands of stars, catalogued clusters and clouds, and the slow architecture of the spiral arms. The Milky Way was vast and ancient and still full of questions, yes. But it felt knowable. Then something changed. In 1990, an astronomer named Charles Bruce Stephenson was working through data from a wide-field infrared sky survey. Infrared, meaning a form of light that lies just beyond what human eyes can detect, wavelengths too long to register in the eye's receptors, but real, measurable, and crucially, capable of passing through dust that blocks ordinary light completely. While reviewing that data, Stephenson noticed a cluster of stars in one of the most obscured regions of the entire galaxy, bright, even in infrared, a dense concentration of objects in a part of the sky that visible light telescopes had essentially treated as empty. He catalogued it. He gave it a number. Stephenson, too, he had no idea what he had found. The cluster sits deep inside the Scutum-Centaurus arm, one of the great spiral arms of the Milky Way, a broad, sweeping river of stars and gas and molecular cloud that curves through our galaxy at a distance of roughly 20,000 light-years from Earth. 20,000 light-years. Let's hold that for a moment, because that number deserves to land properly. Light travels at roughly 300,000 kilometers, or about 186,000 miles, every single second. That is fast enough to circle the entire Earth 7.5 times in the time it takes to blink. Even at that speed, crossing the distance to Stephenson, too, would take 20,000 years. Think about what was happening on Earth 20,000 years ago. The last great ice age was near its peak. Glaciers more. Then a kilometre thick covered much of North America and Europe. Woolly mammoths walked across frozen plains from Siberia to the British Isles. The earliest traces of cave paintings, those quiet, remarkable marks humans left on stone walls, were only a few thousand years old. Modern humans had barely begun spreading across the planet. A beam of light that left the Stephenson 2 cluster at that exact moment in Earth's history would only now be arriving here, tonight. That is the distance we are dealing with. And yet the distance alone is not why this region stayed hidden for so long. The reason is dust. Not the thin haze in an unswept room. Not even the grey obscurity of a desert sandstorm. The dust in the Scutum-Centaurus arm consists of vast molecular clouds, enormous regions of gas and microscopic solid particles, carbon, silicates, ice crystals that stretch across thousands of light years. When visible light from stars behind those clouds attempts to travel toward us, those particles absorb and scatter it. The starlight simply never arrives. To an optical telescope, any instrument designed to collect ordinary visible light, the same wavelengths your eyes evolved to detect, that entire swath of the Milky Way looks nearly empty. A dark band, a gap, a wall. Think of it this way. Imagine trying to see a single candle burning on the far side of a mountain range made entirely of dense fog. You cannot. The fog absorbs the light before it ever reaches you. That is what the dust in the Scutum-Centaurus arm does to everything behind it. For as long as humans have been observing the sky, the stars in that region might as well not have existed. They were sending light outward in every direction. We simply had no tools to receive it. Infrared light changes that equation. The longer wavelengths pass through dust more easily, not perfectly, not without some dimming, but enough to detect what is behind the wall. Think of the gentle warmth you feel from a fireplace before you've turned to look at it, radiating through the air and reaching your skin. That is infrared, not visible, but real. And in 1990, when Stephenson's survey captured infrared emissions from that shadowed arm, the wall cracked open. Just enough. How many other objects are hiding behind dust clouds we haven't yet found the right tools to see through? We don't know. That question still has no answer. And that, in itself, should give us pause. Stephenson wasn't hunting for records. He was doing what working astronomers actually do most of the time: cataloguing, sorting, flagging objects of interest in long columns of data. The survey he was using wasn't designed to find anything in particular. It was a broad sweep, a general inventory of infrared emissions across the sky. When the cluster appeared in the data, it looked like a modest grouping, a handful of bright infrared sources sitting close together, dense perhaps, but not obviously spectacular. He logged it, numbered it, moved on. The astronomical community largely did the same. It would be more than a decade before anyone looked closely again. In the early 2000s, a team of researchers re-examined the Stephenson 2 region using significantly improved infrared instrumentation. What they found made them look twice. Then again. The cluster wasn't modest. Stephenson 2 contained an extraordinary concentration of red supergiants, a class of star so enormous and so evolved that most astronomers expect to find perhaps one or two in any given region of space, if they're fortunate. Red supergiants are what happens to the most massive stars late in their lives. A star begins as a brilliant, hot, blue giant, burning through hydrogen fuel at a ferocious rate. As that fuel runs low, the core contracts and heats, but the outer layers respond by expanding outward, swelling to dimensions almost beyond comprehension, cooling as they spread, shifting from hot blue to deep, muted, red. They are rare, they are brief, and they are enormous. Stephenson 2 contained more than 20 of them, 20 red supergiants within a single cluster. The probability of that arising by chance is so low that the research team initially questioned their own measurements. The cluster became recognized as one of the richest concentrations of red supergiants ever identified in the Milky Way, perhaps in any observed galaxy. Something in this region had triggered an extraordinary burst of massive star formation at nearly the same moment in cosmic history, and those stars had evolved together in rough lockstep into their red supergiant phase. That discovery alone was remarkable, but it turned out to be only the preface. Among those 20-plus red supergiants, one kept returning strange values. Not strange in the sense of an instrument error, strange in the sense of a measurement that didn't fit. Astronomers working through each star in the cluster, estimating the temperature at each stellar surface, measuring each star's infrared brightness, calculating each one's total energy output, found that one member of the cluster consistently produced numbers that sat far outside what the others showed. Its luminosity, the total power radiating outward from its surface, the combined energy it pours into space every second, was staggering. When combined with estimates of its surface temperature, the numbers pointed toward a stellar radius that challenged what the standard models of stellar physics said was possible. The star was designated Stephenson 2-18, an unremarkable label, a filing number, a placeholder. And here is what makes the early period of this discovery quietly extraordinary. The astronomers who first flagged this star did not immediately stand up and announce they had found the largest star ever measured, because the honest answer, at that moment, was that they weren't certain. The distance to the cluster was still being debated. The measurements were preliminary. Every value they had came with an error bar, a margin of uncertainty that was itself enormous. Stephenson 218 was hiding behind 20,000 light-years of space and centuries of accumulated cosmic dust, and every number describing it was still fighting its way through that uncertainty. Science doesn't announce records casually. It builds the case, carefully, methodically, and the case for Stephenson 218 would take years. Right now, wherever you are, the weight of your body is pressing gently against whatever is beneath you. The bones holding that weight contain calcium. The blood moving quietly through your veins carries iron. The air filling your lungs with every breath holds nitrogen and oxygen. Every one of those elements, the calcium, the iron, the nitrogen, was forged inside a star. Not this star. Stars that lived and died billions of years before the sun existed. Your body is made of matter that passed through the core of a collapsing giant, was blasted outward in a supernova explosion, drifted through interstellar space for millions of years, collapsed into a cloud, and eventually found its way into the planet you were born on. We had always known stars were important to life, but until we found Stephenson 2, until infrared light revealed what ordinary eyes could not see, we had no idea that 20,000 light-years away, behind a wall our instruments couldn't penetrate, something was waiting. Something so large it would force astronomers to revisit what they believed a star could be. We had found the cluster, we had identified the outlier. We had a name, Stephenson 2-18. But a name is not a measurement, and a flag is not a size. The real work, the years of refined observations, improved distance estimates, more precise temperature readings, and increasingly careful application of stellar models, was still ahead. And when that work finally converged on an answer, when the data was as clean as it was going to get and the number settled into place, what came back was not what the models predicted, not slightly beyond expectations, not a modest outlier at the upper edge of what theory allowed. The radius of Stephenson 218, based on the best available measurements, was approximately 2,150 times the radius of our Sun. That number needs a comparison, because stated alone, it means almost nothing. To understand what 2,150 solar radii actually feels like, to truly grasp what kind of object we're talking about, we need to bring this star home. We need to place it in the center of a solar system we already know. We need to see what it would swallow. The number had settled. 2,150 times the radius of our Sun. That was the measurement. And for a moment, working astronomers simply stared at it. Because a number like that doesn't mean anything, not immediately. Not until you bring it home. We have a tendency, when confronted with enormous numbers, to nod politely and move on. 2,000 solar radii. Fine, large, understood. But the nod is a lie. The number hasn't landed. The mind has accepted the words without accepting the reality they describe, and there is a significant difference between those two things. So let's not nod. Let's actually go there. Let's place this star at the center of our solar system, the exact position our Sun occupies right now, and watch slowly, deliberately, what happens. Before we can understand what Stephenson 218 would do to our solar system, we need to genuinely feel how large our Sun already is. Because most people underestimate it considerably, our Sun has a radius of roughly 696,000 kilometers, or about 432,000 miles. That is the distance from the Sun's core to its surface. To walk this distance at a slow, steady pace, never stopping to rest, would take 80 years. A human could be born at the heart of the Sun, spend their entire life moving toward the edge, and pass away from old age just as they finally reach the light of the surface. And yet the Sun fits inside Stephenson 2-18 roughly 10 billion times over. 10 billion. That means if you hollowed out Stephenson 218 and began filling it with suns the way you might fill a jar with marbles, you could pour in our entire sun, one complete star, the source of all light and warmth on Earth, and it would represent 1/10,000,000th of the available space. You would need to do that 10 billion times before the jar was full. That number needs a physical anchor before we go any further. Imagine the sun shrunk down to the size of a tennis ball, a standard tennis ball, roughly 6.5 centimeters across, the kind that fits easily in a closed hand. At that scale, our solar system becomes something you could walk across in an afternoon. Earth would sit about 7 meters, the length of a large room, from the center of that tennis ball. Now, at that exact same scale, Stephenson 218 would measure approximately 140 meters across. That is roughly the length of a large aircraft carrier, or, if you prefer, imagine a 40-story building lying on its side. That is the width of this star at the scale where our sun fits in your palm. You are holding a tennis ball. The star we are discussing is a skyscraper, and Earth's orbit. At that scale, Earth would be sitting roughly 7 meters from the tennis ball's surface, which means if you replace the tennis ball with the scaled version of Stephenson 218, Earth's entire orbit would fall deep inside the star's body, roughly 63 meters from the surface, buried within the star's outer layers. This is not a metaphor for something distant. This is what would actually happen. Let's walk through it properly, planet by planet. Before we do, take a moment. Try to guess where you think the star's surface would fall. Which planet marks the outer boundary? Uranus? Neptune? Somewhere between them? Hold that guess. We begin at Mercury, the closest planet to our Sun, orbiting at roughly 58 million kilometers, 36 million miles, from the center of the solar system. Stephenson 218's surface would lie more than 1.5 billion kilometers beyond that point. Mercury vanishes. Instantly. Not vaporized by heat in this thought experiment, simply swallowed, absorbed into the body of the star before we've even begun. Venus, 108 million kilometers out, gone. Earth, our planet, 149 million kilometers from the Sun, the exact distance that makes liquid water stable on our surface, the precise orbital radius that produced every living thing that has ever existed. That distance represents less than 1/10 of the radius of Stephenson 218. Earth is gone. Mars, 228 million kilometers. Gone. Now we reach Jupiter, the largest planet in our solar system, a world so vast that all other planets combined could fit inside it twice over. Jupiter orbits at 778 million kilometers from the Sun. That sounds like enough distance. Surely Jupiter survives. Gone. The surface of Stephenson 218 sits at roughly 1.5 billion kilometers from its center. Jupiter's orbit ends hundreds of millions of kilometers short of that boundary. Saturn is the last question. Saturn, with its extraordinary ring system, orbits at approximately 1.43 billion kilometers from the Sun. The star's surface, at 1.5 billion kilometers out, extends just beyond Saturn's path. Saturn too falls inside the star. Only Uranus, at nearly 3 billion kilometers out, orbits clear of the surface. Mercury, Venus, Earth, Mars, Jupiter, Saturn, 6 planets, gone. Picture yourself standing where Earth stands now, 149 million kilometers from the center of this star. In our solar system, that position places you in open space, warmed by a distant sun that fills a small circle in the sky, bright and brilliant, but clearly finite. You can look in any direction and see stars, darkness, the cosmos. Now replace the Sun with Stephenson 218. You are no longer in open space. You are inside a star, in every direction, above, below, to your left, to your right. The surface of the star is nowhere near you. You are not near the edge. You are deep within the outer layers of the star's body, and the surface is still over 1,300,000,000 kilometers away. The star does not fill part of the sky. The concept of sky has no meaning you exist inside a vast, slowly churning ocean of gas and plasma, deep red in color, illuminated from within, extending beyond any horizon your eyes could construct. The redness is not the red of a sunset. It is deeper, older, the color of a fire cooled to its absolute minimum, the deepest glow before darkness, in every direction, endlessly, unbroken. That is where Earth's orbit sits inside this star. Here is one more way to feel this, through something we can reason about even if we cannot feel it directly. Light travels at roughly 300,000 kilometers per second, 186,000 miles per second. Nothing in the universe moves faster. The light leaving our sun right now takes just over 8 minutes to reach Earth, 8 minutes to cross 149 million kilometers of space, to cross the full diameter of Stephenson 218 from one side of the star to the other, that same beam of light moving at the fastest. Speed the universe permits would need approximately 2 hours and 46 minutes, nearly 3 hours, to cross a single star. For context, in those same 3 hours, light from our sun would have passed not just Earth but Mars, Jupiter, and nearly reached Saturn. All of that distance, the entire inner solar system, covered in the time it takes light to travel through this one star's body. The sun crosses its own width in under 5 seconds. 3 hours versus 5 seconds. That is the difference between the largest star we have ever found and the one that made all life on Earth possible. Here is why this is so hard to absorb, and it is worth understanding, because the difficulty is not a flaw in the viewer. The difficulty is built into human biology. Our nervous system evolved to perceive and react to things between roughly 1 millimeter and a few kilometers in size. Threats, food, terrain, other people. The entire useful range of human perception spans perhaps 9 orders of magnitude, from the width of a hair to the horizon on a clear day. Stellar astronomy asks us to hold scales that exceed that range by another 20 orders of magnitude. The human nervous system was never built for this, not because we are inadequate, but because nothing in our evolutionary history ever required it. This is why we nod at large numbers without truly receiving them. The brain produces a placeholder, very large, and moves on, because it has no bucket for the real thing. The only tool we have is analogy, compression, comparison, the tennis ball and the aircraft carrier. Earth's orbit buried inside a star's body, light taking 3 hours to cross what our sun covers in 5 seconds. These are not decorations. They are the only machinery we have for building a genuine mental image of something the nervous system was never designed to hold. And even now, having walked through all of it, the planets, the light travel time, the deep red interior, the true scale of Stephenson 218 remains, at some fundamental level, beyond reach. That is not a failure of imagination. That is the honest measurement of what this star represents. Deep red, not the red of a warning sign or a fire engine, something far older and quieter than that. The color of an ember that has been cooling for 1,000 years, still warm, still radiating, but reduced to its most ancient frequency. That is the surface color of the largest known star in the universe. Right now, the air in the room around you is at room temperature, warm enough to feel against your skin, stable, unremarkable. The molecules moving through that air were forged in stellar cores. The carbon in your body was built in a star somewhat smaller than Stephenson 218, but enormously larger than our sun. You are, in a very literal sense, the compressed and cooled remnants of stellar interiors that once resembled what we are describing. The star that would swallow Saturn's orbit is not something alien to your existence. The same physics that governed Stephenson 218 govern the stars that built every atom in your body. We are not observing something foreign. We are reading the operating manual for the process that made us. Stephenson 218 stands at the extreme edge of what we know, but the word extreme only has meaning in comparison, and here is where the story opens into something we didn't expect. Stephenson 218 does not exist alone. It was found inside a cluster, a dense community of red supergiants, each one enormous by any ordinary measure, more than 20 of them, assembled in the same region of space, having lived and evolved in near lockstep for millions of years. And when astronomers began comparing Stephenson 218 not just to our Sun, but to those other giants beside it, to the stars that had previously held the record for the largest known object of their kind, what they found was not merely that Stephenson 2-18 was bigger, it was in a different category entirely. Here is something worth pausing on. Stephenson 218 was not discovered in isolation. It was found inside a community, a dense cluster of stars that were themselves each among the largest objects of their kind ever catalogued. The record holder lived surrounded by giants. When we talk about the largest known star in the universe, the instinct is to think of something singular, an outlier, a lone freak of nature sitting in empty space, anomalous and alone. But that is not the situation. Stephenson 2-18 resides inside the Stephenson 2 cluster, and that cluster contains more than 20 confirmed red supergiants. 20 individual stars, each one so large, so luminous, so far along in its stellar evolution that finding even one of them in a given region of space would be considered unusual. Finding more than 20 in the same cluster is, by the standard metrics of stellar astronomy, deeply strange, and finding that the largest among them dwarfs everything else astronomers had previously measured, that is where strange becomes something else entirely. To understand why Stephenson 218 stands where it does, we need to understand the company it keeps. Red supergiants are not common. The universe produces them rarely and briefly. A star must be born with a mass somewhere between roughly 8 and 40 times the mass of our Sun, massive enough to exhaust its core hydrogen at a ferocious rate, but not so massive that it collapses or explodes before reaching its red supergiant phase. And that phase itself is fleeting. On the timescale of stellar lives, which span millions to billions of years, the red supergiant phase lasts only a few 100,000 years at most. A blink, an eye blink in a life already short by cosmic standards. Think of it this way. Imagine a city where every building has a lifespan, and the tallest skyscrapers, the ones that dominate the skyline, exist for only a few days before they are demolished and replaced. If you walked through that city and found an entire block where 20 of those short-lived skyscrapers all happened to be standing at exactly the same moment, you would know something remarkable had happened on that block. Some unusual concentration of construction activity, some coordinated burst of building, had left them all standing simultaneously in defiance of the odds. That is what the Stephenson 2 cluster represents in stellar terms. More than 20 massive stars were born in the same region, at roughly the same time, from the same enormous molecular cloud, a cloud of gas and dust so massive that it seeded dozens of high-mass stars in a single burst of formation. Those stars evolved together, burning through their fuel in near lockstep, and arrived at the red supergiant phase within a narrow window of cosmic time. We happen to be looking at that window right now. A few million years from now, they will all be gone, exploded, collapsed, scattered. Future civilizations, if they look at this region of the galaxy, will find nothing here but remnants and silence. We are watching a brief, unrepeatable assembly. But knowing the cluster is extraordinary doesn't tell us how extraordinary Stephenson 218 is within it, or how it compares to every other large star astronomers had previously identified. For that, we need to go back a little. For many years, two stars dominated discussions of stellar size records. The first was VY Canis Majoris, a red hypergiant in the constellation Canis Major, roughly 3,890 light-years from Earth. That distance is close enough, in astronomical terms, that telescopes could study it in considerable detail. For decades, estimates placed VY Canis Majoris at somewhere between 1,800 and 2,100 solar radii, numbers large enough that it appeared routinely in lists of the biggest known stars, in textbooks, in popular science articles. The name became familiar. But as measurement techniques improved, the picture shifted. More precise observations, using refined methods and better calibrations of the star's distance, produced revised estimates. By the early 2010s, the consensus had moved VY Canis Majoris down significantly, to roughly 1,420 solar radii. That is still almost incomprehensibly large, but the earlier figures had been overestimates, and the revision mattered. Then there was UY Scuti. For a period, UY Scuti was the name, the record holder. The star that appeared in infographics, in YouTube comparisons, in school presentations about stellar scale. Located about 9,500 light-years away in the constellation Scutum, the same general region of the sky as the Stephenson 2 cluster, which is worth noting. UY Scuti carried estimates of roughly 1,500 to 1,700 solar radii, depending on the study consulted and the error bars accepted, and those estimates deserve to land properly. 1,500 solar radii means a star whose surface, if placed at the centre of our solar system, would reach past the orbit of Mars, past Jupiter, closing on Saturn. By any reasonable measure, UY Scuti was a genuinely extraordinary object, and the people who called it the largest known star were working from legitimate data. For years, that record felt stable. But here is the problem with records in astronomy. We only know about what we can see, and what we can see is limited by our instruments, our survey coverage, and, critically, by what the dust between us and distant stars allows through. A significant fraction of the Milky Way sits behind dust walls that ordinary telescopes cannot penetrate, and in those hidden regions, large stars might exist in numbers and sizes we have no current knowledge of. Stephenson 2-18 came from exactly one of those hidden regions, when researchers consolidated the best available measurements of Stephenson 2-18 using infrared data, improved distance estimates, and spectroscopic analysis. The radius that emerged was approximately 2,150 solar radii, not slightly larger than UY Scuti's best estimates. The gap between Stephenson 2-18 and the previous record holder, measured in solar radii, is itself larger than the vast majority of stars in the Milky Way. The difference alone, roughly 400 to 600 solar radii depending on which estimates you use for UY Scuti, would, if it were a standalone star, be one of the largest known objects of its kind. Stephenson 2-18 didn't nudge the record forward. It moved it by a margin that is itself enormous. Picture yourself placed somewhere inside the Stephenson 2 cluster, not near any one star, but in the open space between them, looking outward in all directions. In every direction, deep red light. More than 20 red supergiants, each burning at a surface temperature of only 3,000 to 4,000 degrees, cool by stellar standards, which is why they glow red rather than white or blue, and each one so large that if any of them replaced our Sun, it would swallow at least Earth's orbit. You are surrounded by giants, and then you turn toward one that is larger than all the others, not slightly larger, not the way the tallest person in a room is taller than those around them, larger the way a mountain is larger than the hills at its base. You cannot see its full extent. The surface is hundreds of millions of kilometers away in every direction. The light reaching you is ancient, deep, dark red, the color of something that has been burning for millions of years and is only now reaching its fullest and most fragile expansion. That is Stephenson 2-18, inside a cluster of giants, and still a category apart. Here is something that needs to be said plainly, because serious astronomy requires it. All of these numbers, 2,150, solar radii for Stephenson 2-18, 1,500 for UY Scuti, 1,420 for VY Canis Majoris, carry significant margins of uncertainty. Measuring the radius of a star is not like measuring a room with a tape measure. Astronomers cannot resolve these stars as visible disks. They cannot send a probe. Every measurement is indirect, filtered through layers of inference, dependent on distance estimates that themselves carry error. and complicated by the fact that these stars don't have clean, well-defined surfaces in the way a solid object does. Some researchers argue that when the full error ranges are taken into account, the uncertainty bands that bracket every measurement, the rankings could plausibly shift. UY Scuti's radius, under some calculations with generous error margins, reaches values that overlap with lower estimates for Stephenson 2-18, and Stephenson 2-18 itself, at the lower end of its uncertainty range, could come in closer to 1,800 solar radii, still enormous, but less dominant over the competition. We don't know, with certainty, which of these stars is definitively the largest. What we do know is that Stephenson 2-18's best current estimate places it at the top of every serious compilation, and we know that the gap is large enough that it would take a significant revision, a genuine recalculation of its distance or its physical properties, to displace it. The record is real, but like all records in astronomy, it is also provisional. The universe has not yet shown us everything. 20 dying suns burning slowly in the same patch of sky. Not the sharp white of a young star, something older than that, deeper, like light that has been travelling through too much time to retain its urgency. What Stephenson 2-18 represents, in the context of stellar physics, is not just a size record. It represents a boundary, a region of stellar behaviour where the standard models of how stars form, expand and hold themselves together begin to strain under their own assumptions. Stars exist because of a balance, gravity pulling inward, radiation pressure pushing outward. In a stable star, those two forces are in equilibrium. The star neither collapses nor explodes. But as a star expands into the red supergiant phase, that balance becomes increasingly precarious. The outer layers grow so large, so diffuse, so loosely bound to the core, that gravity's grip on them weakens considerably. The star is not so much holding itself together as slowly losing its grip on itself. At 2,150 solar radii, Stephenson 2-18 sits at the very edge of where that balance can be maintained, or possibly slightly beyond it. Based on current estimates, this is approximately the largest size stellar physics permits before a star begins to lose mass faster than it can sustain itself. It is not merely the largest known star, it may be close to the largest possible star of its type. That distinction matters. Finding the largest known anything is interesting. Finding something at the physical limit of what nature allows, that is a different kind of discovery. And yet, all of this rests on a number. 2,150 solar radii, a figure that has appeared repeatedly in this story, that we have used to walk through the solar system and compare against every other known giant. But we have not yet asked how that number was actually obtained. 20,000 light-years away, hidden behind dust for most of human history. No telescope on Earth or in orbit can see Stephenson 2-18 as a disk. It is too distant, too obscured, too small in angular terms to resolve directly, the way you might see the surface of the moon. The number we have been working with this entire time was not measured directly. It was calculated, inferred, built from a chain of observations and assumptions, each one dependent on the accuracy of the last. And that chain is more fragile and more ingenious than most people realize. The story of how astronomers arrived at that number is itself extraordinary, because measuring something you cannot see at a distance you cannot cross, using tools that were never designed to do exactly this, that is not a limitation of science. That is science at its finest. We have been using a number, 2,150 solar radii. We have walked through entire solar systems with it. But at some point, a fair question demands an answer. Where did that number actually come from? Because no one has ever seen this star's edge. There is a particular kind of confidence that science earns, not the confidence of certainty, but the confidence of methodology. The confidence of knowing exactly how you arrived at an answer, and exactly how much trust that answer deserves. That kind of confidence is harder to build than it sounds, and for a star hidden behind 20,000 light-years of dust and space, building it requires something close to an act of collective human ingenuity that has unfolded across decades. But here is the thing that tends to surprise people when they first encounter it. No telescope on Earth, and no telescope currently in orbit, has ever seen Stephenson 218 as a disk, not as a circle of light with a measurable edge, not as a resolved sphere the way we see the Moon, or the way interferometers have resolved a handful of very nearby giant stars. The star appears in our instruments as a point, a bright infrared dot against the background of the sky. And from a single point, you cannot read a size directly, not without a chain of reasoning that is, when you follow it carefully, quietly extraordinary. Right now, your eyes are open. Light is arriving at them, bouncing off the surface you are reading, carrying information about color and shape and distance directly into your visual cortex. That process feels immediate, passive, effortless, but your eye has limits. The human eye can distinguish two separate points of light only if they are separated by an angle of at least about 1 arc minute, 1/60th of a degree. Anything closer together than that angle, and the eye merges them into one, a single dot. At the distance of Stephenson 218, 20,000 light-years, the angular diameter of the star, the tiny angle it subtends against the background sky, is roughly 3/10,000ths of a single arc-second. To put that in perspective, that is roughly the same angle a single human hair would occupy if it were viewed from more than 70 kilometers away. That is an angle so small it would require a telescope, with a resolving power roughly 10,000 times finer than the best ground-based optical instrument to detect it directly. The star is not invisible, but its size, its physical edge, its actual boundary as a measurable disk, that is invisible to every instrument we currently have. And yet we have a number, a remarkably precise number. How? The answer lies in a technique that runs throughout astronomy whenever direct measurement fails, which is most of the time. Instead of measuring the star itself, astronomers measure everything around it that they can measure, and then calculate what the star must be. Think of it this way. You are standing in a valley on a cloudy night, and you cannot see a mountain on the far side of the valley. But you know how far away the mountain is from a map. You have a photograph taken from a balloon that shows the mountain's silhouette against the clouds. From the photograph, you can measure the angle the mountain occupies in the image. And from the angle combined with the known distance, you can calculate the mountain's height exactly, without ever seeing it directly, without ever touching it. That is the structural logic of indirect stellar measurement. Replace the mountain with a star. Replace the balloon photograph with a spectrograph. Replace the map distance with a parallax measurement. The chain of inference is longer and more demanding, but the principle is identical. The first crucial link in that chain is spectroscopy. A spectrograph is an instrument that takes the light arriving from a star and spreads it out by wavelength, separating it into its component colors the way a prism splits white light into a rainbow. Except the rainbow from a star is not smooth and continuous. Running across it, at precise and specific positions, are dark lines, gaps in the spectrum where certain wavelengths of light have been absorbed. Imagine that a neighbor is cooking something in their kitchen a few houses away. You cannot see into their kitchen, but you can smell the smoke rising from their chimney. And if you are a chemist, you can identify exactly which compounds are present in that smoke, which tells you, with considerable precision, what is burning. You have read the kitchen without entering it. That is what spectroscopy does with starlight. Each chemical element, hydrogen, helium, titanium oxide, water vapor, absorbs light at its own unique set of wavelengths. The dark lines in the spectrum are those absences, and from their positions and strengths, astronomers can identify which elements are present in the star's outer layers, and crucially, what temperature those layers are burning at. A star's spectrum is its fingerprint, unique, permanent, and readable from 20,000 light-years away. For red supergiants like Stephenson 2-18, the spectrum reveals a surface temperature of roughly 3,000 to 4,000 degrees. 3,000 degrees sounds hot. By stellar standards, for a star of this size, it is barely warm, comparable to the temperature of the coil on an electric stovetop at maximum heat. For reference, our Sun's surface runs at about 5,500 degrees. Stephenson 218 burns cooler and larger, a vast, diffuse, deeply red object by the standards of stellar physics. Surface temperature alone does not give a size, but temperature combined with luminosity does. Luminosity, meaning the total energy a star radiates outward every second in all directions, is something astronomers can estimate from how bright the star appears in our instruments, corrected for the distance to the star, and the dimming caused by the dust between us. And here is a relationship that runs through all of stellar physics, like a structural beam. A star's luminosity depends on two things, and only two things: its surface temperature and its surface area. A hotter star radiates more energy per square meter of surface. A larger star has more square meters of surface. Together, temperature and luminosity constrain the radius. And if you know two of those three quantities precisely enough, you can solve for the third. It is the same principle used to estimate the wattage of a light bulb if you know both how bright it appears and how far away it is. You measure the brightness at your position, calculate how far the light has travelled, and work backward to determine how much power was emitted at the source. The math is more involved for stars, the corrections for dust, for distance uncertainty, for the star's exact spectral type. But the underlying logic is unchanged. Luminosity and temperature give radius. But that whole calculation rests on one foundation that must be solid before anything else can stand: the distance. If the distance to Stephenson 2-18 is wrong, if the cluster is 10% closer or 10% farther than estimated, then the luminosity calculation is wrong and the radius that emerges from it is wrong by a corresponding margin. Distance is not just one variable in the chain. Distance is the keystone. And measuring distances to objects 20,000 light-years away, hidden behind dust that absorbs and scatters the very light astronomers need to measure, is one of the hardest problems in observational astronomy. This is where the ESA Gaia mission enters the story. Gaia is a space telescope launched in December 2013, designed to do one thing with exceptional precision: measure the positions and motions of stars. Not their spectra, not their brightness in isolation, but their exact location in the sky, measured over and over again as Earth orbits the Sun. As Earth moves from one side of its orbit to the other, nearby stars appear to shift very slightly against the background of distant stars. That shift, called parallax, is the same effect you notice when you hold up a finger close to your face and alternately close each eye. The finger appears to jump against the background. The amount of jump tells you how far away the finger is. The smaller the jump, the greater the distance. Gaia measures this parallax shift for over 1 billion stars across the galaxy, and its precision is genuinely difficult to comprehend. The spacecraft can detect positional shifts as small as 24 microarcseconds, an angle equivalent to the apparent size of a coin, roughly the diameter of a euro placed at the distance of approximately 200,000 kilometers, or about 124,000 miles. That is roughly half the distance from Earth to the Moon, detecting a coin at half the lunar distance from a telescope drifting in space as a measurement precise enough to calculate the location of a star. That is the standard Gaia is working at. For the Stephenson 2 cluster, Gaia's observations, particularly those released in the third major data release in June 2022, have substantially improved the distance estimates, not resolved them perfectly. The cluster sits deep behind dust, which dims and reddens the stars and introduces its own source of measurement uncertainty. But the distance picture is considerably sharper now than it was before Gaia flew. You have a photograph of a distant mountain taken through thick fog. You know roughly how far away the mountain is, within perhaps 15% accuracy either way. From the photograph, you can estimate the angle the mountain occupies, and from those two inputs, a rough distance and a measured angle, you can calculate a height. but your answer carries the uncertainty of both inputs. If the distance is off by 15%, your height is off by 15%, and if the fog has distorted the apparent outline, adding a halo of scattered light around the summit, your angle measurement is also uncertain. The height you calculate is real. It is the best available number. But it is not the final word. That is exactly the position astronomers occupy with Stephenson 2-18. The measurement is real, the methodology is sound, but the number comes with a range, and that range matters. The current best estimates for the radius of Stephenson 2-18 span a range from approximately 1,800 to 2,400 solar radii, depending on which study's distance and temperature assumptions you accept. The central estimate, the value that appears most often in the literature and that we have been using throughout, sits at roughly 2,150 solar radii. But 1,800 is also defensible, and 2,400 is also defensible. That spread, 600 solar radii, is wider than the entire radius of most stars ever considered for a size record. The uncertainty band for this single star is larger than most of the competition. Here is the honest statement that science requires. We do not know the exact radius of Stephenson 2-18. We have a best estimate, we have a methodology for arriving at it, and we have a range that brackets the reasonable possibilities. That is not a failure. That is what honest measurement of an object, this distant, this obscured, and this physically complex actually looks like. And the physical complexity goes deeper still. Red supergiants, and Stephenson 2-18 almost certainly among them, do not hold a fixed size. They pulsate, they breathe in a sense, expanding and contracting over timescales of months to years, driven by complex oscillations in their outer layers. The radius of such a star at one point in its pulsation cycle can differ meaningfully from its radius at another point. When different research teams observe the star at different times using different instruments and calculate different radii, part of that disagreement may not be methodological error at all. Part of it may be that the star genuinely changed size between observations, and there is a deeper complication. The question, where does the star end, is not as simple as it sounds. A solid object has a clear surface, the edge of a rock, the wall of a building. These boundaries are unambiguous. But the outer atmosphere of a red supergiant is not solid, not even gas in any ordinary sense. It is an extraordinarily diffuse region, so thinly spread that the density of the outermost layers is far lower than the best vacuum achievable in any laboratory on Earth. The boundary between star and space is not a wall. It is a gradual thinning, a fading, like the edge of a fog bank that has no clear outer limit, only a region where the fog becomes too thin to see. Astronomers define the stellar radius as the distance from the center to the photosphere, the layer at which the star becomes opaque to outgoing light, the layer from which the light we detect is actually escaping. But even that definition involves some judgment. The photosphere of a red supergiant is itself a broad, irregular, slowly churning region rather than a sharp sphere. Different wavelengths of light escape from slightly different depths. The star has no single, clean, agreed-upon edge. What this means is that the number, 2,150 solar radii, is not a measurement of a physical boundary in the way we measure a table's length. It is the best current estimate of a fuzzy statistical edge on a pulsating, diffuse, slowly dying object 20,000 light-years away. It is the most honest answer we can give with the tools we currently have. A thin, dark line, barely visible in a rainbow of color spreading across a detector. Quiet, precise, permanent, the chemical signature of titanium burning in the atmosphere of a star we will never visit, telling us the temperature with a clarity that nothing else could. But here is what is worth pausing on, because there is something genuinely remarkable in what we have just described. A star hidden behind 20,000 light-years of dust and space, never resolved as a disk, never visited, never directly touched by any instrument or signal we have sent outward. And yet, from a point of light on a detector, Through a chain of spectroscopic analysis, luminosity calculation, parallax measurement, and careful modeling, a team of human researchers arrived at a number that tells us this object is large enough to swallow the inner solar system, large enough to place it at the extreme edge of what stellar physics permits, large enough to be considered, provisionally, carefully, honestly, the largest known star in the universe. The uncertainty is real. The range is wide, and the number may shift as Gaia's data improves, as better infrared instruments come online, as models of red supergiant atmospheres become more refined. The James Webb Space Telescope, with its unprecedented infrared sensitivity, may contribute measurements of the Stephenson 2 cluster that narrow these values further. We are living in the period when this measurement is still being refined. Future generations of astronomers, with instruments we have not yet built, will likely know this star's radius with a precision we cannot currently achieve. We occupy the imprecise middle, after discovery, before certainty, and that in itself is a remarkable place to be. The measurement is as good as we can currently make it. The star is real. The size is, within its honest range of uncertainty, genuinely extraordinary. But none of that tells us how it got there. A star this large did not arrive in one step. Every object in the universe has a history, a sequence of physical processes, each one following from the last, that carried it from a formless cloud of hydrogen to whatever it is today. And the history of a star like Stephenson 218 is not simply a story of growth, it is a story of transformation, of a star born one way and becoming something almost unrecognizable, passing through phases, shedding identities, swelling outward as its core does something quiet and catastrophic, far from the surface. To understand what Stephenson 218 is, we have to understand what it was and what it went through to get here. Something built Stephenson 2 to 18, not gradually, not gently, through a sequence of physical events, each one following inevitably from the last, each one irreversible, each one driving the star further from what it began as. To understand the size, we have to go back to the beginning. Here is something that cuts against intuition. The most massive stars in the universe are not the longest lived. The relationship runs exactly backward from what common sense might suggest. A star with more fuel, more mass, more hydrogen, does not burn longer, it burns faster. And it burns itself into transformation on a timescale that, measured against cosmic history, is almost shockingly brief. Our Sun will live for roughly 10 billion years in total. The star that eventually became Stephenson 2-18 likely lived its initial phase, its main sequence life, the stable burning period all stars go through before things begin to change, for somewhere between 5 and 8 million years. That is roughly 1,000 times shorter than the Sun's expected lifespan. 5 million years ago on Earth, the first members of the human ancestral lineage, early hominids, beginning to diverge from the great apes, were just appearing. Our entire evolutionary history, everything that led from those first tentative upright steps to the civilization-building telescopes that found Stephenson 218, fits inside the lifespan of its progenitor star. That is how fast a star this massive burns through its fuel. And that pace, that furious, unsustainable rate of consumption, is the first cause of everything that followed. Imagine two fires burning side by side. The first is a modest campfire, careful, well-tended, a few logs feeding it at a slow and steady rate. It burns through the night and into the morning. The second fire is a bonfire, a week's worth of timber thrown onto a single pile, blazing with enormous heat and light, visible from a kilometre away. The bonfire burns brilliantly, but it consumes itself in hours. By the time the campfire is still quietly burning at dawn, the bonfire is cold ash. A massive star is the bonfire. Our Sun is the campfire. The reason is gravity. A star is, at its core, a balancing act between two forces that oppose each other continuously. Gravity pulls the entire mass of the star inward, compressing it, heating it, accelerating the nuclear reactions in its core. Radiation pressure, the outward force generated by those same nuclear reactions, pushes back against gravity, keeping the star from collapsing on itself. In a stable star, these forces are in equilibrium. The star neither expands nor contracts, it simply burns. But the more massive the star, the stronger gravity's inward pull, and the more furiously the core must burn to counteract it. A star of 25 to 40 solar masses, the likely birth mass of the progenitor of Stephenson 2-18, must generate energy at a rate millions of times greater than our Sun just to maintain that equilibrium. And generating energy at that rate means consuming fuel at that rate. The core burns through its hydrogen not over billions of years, but over millions. In its earliest and most stable phase, the progenitor of Stephenson 2-18 almost certainly looked nothing like what we see today. A young, massive star burns hot, enormously hot. Surface temperatures of 30,000 to 50,000 degrees. That kind of heat radiates at the blue and ultraviolet end of the spectrum. The star would appear to human eyes as intensely blue-white, the hottest color visible light can carry. A brilliant, compact, ferociously energetic object, not particularly large by the standards of red supergiants, but radiating so much energy per square meter of surface that its total luminosity would outshine the Sun by hundreds of thousands of times. Blue-white, compact, furious. That was the beginning, and then slowly at first and then with accelerating. Consequence: the hydrogen in the core began to run out. The core of a massive star burns hydrogen into helium through nuclear fusion, a process where atomic nuclei are forced together under the extreme pressure and temperature of the stellar center, releasing energy as they merge. Helium is the ash, and unlike wood ash, which simply accumulates and cools, the helium ash in a stellar core has weight, enormous weight, and as it accumulates, something critical begins to change. The core can no longer fuse helium, not yet, not at the temperatures it currently reaches. So the helium ash sits there, inert, accumulating. The core loses its energy source, and the moment a stellar core loses its energy source, gravity wins, temporarily. The core begins to contract, slowly at first, then faster, compressing under the weight of everything above it, heating as it compresses the way a bicycle pump heats when you force air through it. But here is the part that seems almost paradoxical. While the core contracts inward, the outer layers of the star, the vast hydrogen envelope that surrounds the core, respond in the opposite direction. They expand outward. The reason lies in what happens just outside the collapsing helium core. A thin shell of hydrogen surrounding the core, heated by both the contracting core beneath it and the increased energy flowing outward, begins burning. Ignites, hydrogen shell burning, fusion occurring in a layer wrapped around the inert helium interior rather than at the center itself, begins pouring enormous amounts of energy into the outer layers of the star. Think of a building whose basement furnace has been turned off, but whose walls have caught fire from the outside. The interior is cooling while the exterior is receiving far more heat than it ever did before. The outer structure expands outward under that heat pressure, pushed away from the cooling center, swelling as it goes. For the star, this expansion is dramatic and continuous. As the core contracts and the shell burning intensifies, the outer envelope, the vast hydrogen atmosphere of the star, begins to swell outward over hundreds of thousands of years, cooling as it expands, shifting in color from blue-white to yellow to orange and finally to deep red. The surface temperature drops, the radius climbs, enormously, relentlessly. The blue supergiant is becoming a red supergiant, and as it does, its surface temperature falls to somewhere between 3,000 and 4,000 degrees. Cool enough to allow certain molecules to form in its atmosphere, cool enough to glow in the deep, slow red we associate with stellar old age. You are the outer atmosphere of this star, a vast, loosely held cloud of hydrogen and helium, held to the core by gravity that has been weakening for millions of years as the core retreats further and further inward. The core is contracting, its grip on you is loosening, and the energy from the shell burning beneath you is pressing outward, steadily, persistently, pushing you away from the center. You don't feel a sudden explosion. Nothing dramatic announces this process. You simply drift outward into cooler space, expanding gently over timescales longer than any human civilization. The red glow around you deepens as the temperature falls, as you spread across a volume of space that keeps growing. You are now, having traveled outward from a core no larger than a planet, spread across a region larger than the orbit of Saturn. The core that built you is now a tiny, intensely hot object, buried hundreds of millions of kilometers beneath your surface. The two of you barely resemble what you once were together. This raises a question worth sitting with. If shell burning and core contraction drive this expansion, why don't all massive stars swell to the size of Stephenson 2-18? What prevents a star of similar mass from reaching the same extreme radius? The honest answer involves several factors, and not all of them are fully understood. First, the Hayashi limit. Every star has a theoretical maximum radius, determined by the star's mass and the physics of how energy moves through its outer layers. Specifically, how efficiently convection, the churning circulation of hot gas, can transport energy from the interior to the surface. Beyond a certain radius, convection alone cannot carry the energy fast enough, and the star becomes unstable. This boundary, named for the Japanese astrophysicist Chushiro Hayashi, who first described it in the 1960s, sets a ceiling on how large a convective star can become while remaining in gravitational equilibrium. A rough ceiling, a statistical edge, and Stephenson 2-18 appears to sit very close to it. Second, mass loss. As a massive star expands into the red supergiant phase, its outer layers are held with increasingly weakening gravity. Stellar winds, streams of gas flowing continuously off the star's surface, carry mass away into space. If a star loses mass too rapidly during this expansion phase, the process cuts itself short. The outer layers thin out faster than the expansion can sustain, and the star contracts or explodes before reaching maximum size. A star that arrives at its maximum radius as a red supergiant must thread a particular path. Massive enough to expand enormously, but not so subject to runaway mass loss that the expansion is cut short before it reaches its extreme. Stephenson 2-18, by current estimates, managed that path. Probably. The progenitor of Stephenson 2-18 began with a mass somewhere between 25 and 40 times the mass of our Sun. 25 solar masses, meaning a single object containing somewhere between 50 trillion and 80 trillion kilograms of material, all collapsed from a molecular cloud into a single burning sphere. That initial mass is not itself the cause of the extreme size. It is the trigger. The mass determined the rate of burning. The rate of burning determined how quickly the core exhausted its fuel. The core exhaustion triggered the contraction triggered the shell burning, and the shell burning, over hundreds of thousands of years, drove the expansion of the outer layers to a radius that now encompasses what once was a compact, brilliant blue-white star. Size this extreme is not built, it is released. Like a spring compressed and then allowed to extend, the outer envelope of Stephenson 2-18 expanded into the space that the retreating core vacated. The enormity we have been measuring is, in a real sense, the physical record of an internal event, a core collapse happening in slow motion, invisible to any instrument, sealed away behind the star's own body, and the core is still contracting, still heating, still building toward the next threshold, a star burning blue-white at 50,000 degrees. Not the warm yellow of the sun, but something closer to the color of a welding arc, hard and brilliant and pitiless. That was the beginning of what is now the universe's largest known star. The same process that built Stephenson 218 built the atoms inside you. Every element heavier than hydrogen and helium, the carbon, oxygen, nitrogen, calcium, iron, that make up the chemistry of every living thing that has ever existed, was forged inside a star passing through exactly these phases. Core contraction, shell burning, expanding outer layers carrying newly created elements outward into space. Stars like the progenitor of Stephenson 218, burning briefly and intensely and then exploding, seeded the galaxy with the raw material of chemistry, of biology, of consciousness. The process that built the largest known star is the same process that built the atoms in your body. You are reading the origin story of your own physical existence. So the outer layers expanded. The star reached its maximum radius, 2,150 solar radii, based on our best current estimates, pressing against the physical ceiling that stellar physics imposes. But what, exactly, are those outer layers? We have been speaking of the star's atmosphere as though it were simply a very large version of what we know. But the outer body of Stephenson 2-18 is not a scaled-up version of the Sun's surface. It is something far stranger, far more paradoxical, a region so diffuse, so cool, so physically unusual that calling it a stellar surface in any conventional sense requires considerable qualification. The largest known star, as it turns out, is largely empty, and the reality of what fills those 2,000 solar radii is something that takes the story in a direction that nothing in our ordinary experience of stars has prepared us for. Everything we have established about Stephenson 218 so far rests on one assumed premise, that the largest known star in the universe is, in some ordinary physical sense, there, substantial, present, full of material in the way a large object is expected to be full. That assumption needs revising. We have a habit, when confronted with enormous size, of assuming corresponding substance. A large mountain is heavy. A large building contains vast amounts of stone and steel. A large ocean holds more water than a small lake. Size and substance feel like they should track together. The bigger the object, the more of it there is. For Stephenson 2-18, that intuition is precisely wrong. The outer atmosphere of the largest known star, the vast, diffuse shell that accounts for most of its measured radius, the region responsible for the 2,150 solar radii figure we have been carrying through this entire story, is, in any physical sense that matters, nearly empty, not metaphorically empty, not poetically empty, physically, measurably, genuinely empty in a way that contradicts everything the scale of this object implies. And that paradox, enormous beyond comprehension and almost entirely nothing, turns out to reveal more about what Stephenson 2-18 actually is than the size measurement ever did alone. Start with a comparison that anchors the reality of what we are dealing with. The air in the room around you right now, the air pressing gently against your skin, filling your lungs with every breath, has a density at sea level of approximately 1 2/10 kilograms per cubic meter. That is the density we consider, in ordinary life, essentially empty. Breathable air feels like nothing. Walk through it without noticing. The outer atmosphere of Stephenson 2-18 is tens of thousands of times less dense than that. Let that sit for a moment. Not denser than air, tens of thousands of times less dense. A cubic meter of the star's outer layers contain so little material that it would be considered an excellent vacuum by the standards of most laboratory equipment. The fluorescent lights in an office ceiling contain gas at roughly 0.3% of atmospheric pressure, already far thinner than ordinary air. The outermost layers of Stephenson 2-18 make the inside of a fluorescent tube look crowded, and yet this is a star, the largest known star in the universe, emitting light, radiating energy, holding itself together, after a fashion, across a volume 10 billion times that of our Sun. The surface temperature of Stephenson 2-18, or more precisely, the temperature of the photosphere, the layer from which its light escapes, sits at roughly 3,200 degrees. 3,200 degrees sounds hot. In the context of daily life, it is far beyond any temperature a human body could approach and survive. But in the context of stellar physics, 3,200 degrees is remarkably cool. Our sun's surface burns at approximately 5,500 degrees. Young blue supergiants, stars like the progenitor of Stephenson 218 at the beginning of its life, burn at 30,000 to 50,000 degrees. Even ordinary stars older than the Sun run hotter than Stephenson 218's surface, and the core temperatures of massive stars reach 15 million degrees or more, a number so far beyond 3,000 that the surface temperature of this star, by comparison, is barely a whisper of heat. The deep red glow of Stephenson 2-18 is not the colour of an intense fire. It is the colour of fire that has spread so far, cooled so completely, been diluted across such an enormous surface that it has arrived at the lowest temperature at which a stellar photosphere can still radiate visible light. Deep red is the minimum, the last colour before darkness. And at 3,200 degrees, something extraordinary becomes possible inside the star's atmosphere. Something that should not, by intuition, occur inside a star at all. At the temperatures found in most stellar photospheres, individual atoms are stripped of electrons, or moving so fast that any molecule that forms is immediately torn apart by collisions. Stars, at typical stellar surface temperatures, are composed of individual atoms and ions, matter in its most broken down form. Chemistry, in any meaningful sense, does not occur inside them. But at 3,200 degrees, the outer atmosphere of Stephenson 218 is cool enough, just barely, for certain molecules to form and survive. Titanium oxide, a compound of two metallium atoms bonded to one oxygen atom, the same basic chemistry found in white paint pigment, in sunscreen, in the white minerals of certain rock formations. Titanium oxide forms in Stephenson 218's atmosphere because the temperature there has dropped low enough for chemical bonds to persist. Astronomers detect its signature clearly in the star's spectrum, broad absorption bands that stamp the light passing through those outer layers before it reaches our instruments, and there is water vapor. In the outer envelope of the largest known star in the universe, molecules of water exist. Two hydrogen atoms bonded to one oxygen, the same molecular structure that fills the oceans of Earth, that flows in rivers, that constitutes roughly 60% of the human body by mass. Not liquid water, not ice. Water vapor, dissociated and diffuse, existing at the extreme edge of the star's atmosphere, where the temperature has dropped low enough to permit molecular bonding. The outer atmosphere of Stephenson 218 contains the same molecular water as a terrestrial cloud. The chemistry is not alien. The scale is. Imagine a weather system, a large one, the kind that spans a continent, a slow-moving high-pressure system visible from space as a vast rotating mass of cloud and air covering perhaps 2,000 kilometers, or roughly 1,200 miles from edge to edge. A system large enough to dominate the weather across an entire region for days. Now imagine that the convection cell, the churning bubble of rising hot material and descending cool material that drives that weather system, was not 2,000 kilometers across, but 150 million kilometers. 150 million kilometers, the distance from Earth to the Sun, an astronomical unit. That is the scale of individual convection cells in the outer atmosphere of Stephenson 218. Convection cells are the mechanism by which heat moves from the interior of a star outward toward its surface. Hot material rising, releasing energy, cooling, sinking back down in a continuous cycle. In our Sun, these cells are roughly 1,000 kilometers, 600 miles, across. They give the Sun's surface a granular texture visible in high-resolution solar images, thousands of small, bright cells covering the surface like cobblestones. In Stephenson 2-18, based on current models of red supergiant convection developed by researchers, including the team at Uppsala University in Sweden and the Max Planck Institute for Astrophysics, each individual convection cell likely spans roughly one astronomical unit, one complete Earth-Sun distance, a single churning bubble of rising stellar gas, one convection cell, one unit of heat transport, is as wide as the orbit of Earth. The Sun has millions of these cells on its surface at any given moment. Stephenson 2-18, by some estimates, has only a few dozen covering its entire photosphere, each one vast, each one turning over slowly over time scales of months or years, carrying heat from depths we cannot see toward a surface we can barely measure. You reach out a hand, slowly, deliberately, and push it into the outer atmosphere of Stephenson 2-18, not the photosphere, not the opaque inner layers, but the very outermost. Envelope, the edge of what the star considers its own atmosphere. You feel almost nothing. A faint warmth, perhaps, the radiant heat of 3,000 degrees from deep below arriving so diluted, spread across such an enormous volume of space that by the time it reaches this outermost layer, it is barely distinguishable from the heat of a warm room. And resistance? Effectively none. The material your hand is passing through is so sparse that the individual gas particles, hydrogen atoms, helium atoms, titanium oxide molecules, are separated by distances vast even on atomic scales. Your hand moves through it as though through a fog so thin it has forgotten it exists. This is the outer body of the universe's largest known star. This is what the 2000 solar radii measurement is actually measuring. Not solid material, not even gas in any meaningful everyday sense. A vast, luminous, barely present whisper of matter that has spread itself across a volume 10 billion times the Sun's, grown so dilute that chemistry has become possible inside it, and is glowing its slow, deep red simply because there is enough of it, spread across enough surface area, to collectively radiate a light that we can detect 20,000 light-years away. Stephenson 2-18 does not hold this configuration steadily. Like all red supergiants of its type, it pulsates, expanding and contracting over timescales of hundreds to thousands of days, in cycles that are semi-regular rather than perfectly periodic. Semi-regular means neither random nor predictable, somewhere between the two. The star has dominant periods, characteristic timescales on which it tends to pulse, but they shift and drift in ways that resist precise forecasting. The radius at one phase of its pulsation cycle can differ from its radius at another phase by amounts that are themselves enormous by any ordinary standard, potentially hundreds of solar radii of expansion and contraction, oscillating back and forth over the course of months to years. This pulsation is not a smooth, gentle breathing. The outer atmosphere of a red supergiant is believed to be driven by a combination of opacity changes in the outer layers, regions where the gas alternately becomes more and less transparent to outgoing radiation, trapping energy and then releasing it, and by the vast convective flows below the photosphere, which generate turbulence, shocks and pressure waves that propagate outward and drive the surface up and down on timescales that the convection cells themselves set. And here is one of the genuinely open questions of stellar physics, stated plainly. We do not fully understand the pulsation mechanism of red supergiants. The models that describe convection at this scale are computationally extraordinarily difficult, simulating fluid dynamics across distances of an astronomical unit, for material as diffuse as this, with sufficient resolution to capture the physics correctly, remains at the outer edge of what the best supercomputers can manage. The period, amplitude and driving mechanism of Stephenson 2-18's pulsation specifically remain uncertain. This is not a gap in knowledge that will be resolved easily. It is one of the genuinely unsolved problems in the astrophysics of evolved massive stars. The universe has not yet given us a complete answer. Not orange, not the sharp red of a warning light. Something deeper and slower than that, the colour of a coal that has been cooling for 1,000 years in total darkness, still warm enough to glow, barely, in a frequency that human eyes register at the very edge of visible red. The paradox of Stephenson 2-18, enormous in size, nearly empty in substance, is not a contradiction that needs resolving. It is a description, an accurate, physically precise description of what a star becomes when the forces that made it so large are the same forces that made it so diffuse. The expansion that produced the size also produced the emptiness. The same process, core contraction, shell burning, the outer envelope pushed outward over hundreds of thousands of years, that drove the radius to 2,000 solar radii, also spread the available material across a volume so enormous that the density fell to values we would normally associate with vacuum. The star did not grow denser as it grew larger, it grew emptier. Every solar radius of expansion meant spreading the same material across a larger and larger sphere, thinning it further, cooling it further, loosening gravity's grip on it a little more with each passing year. Stephenson 218 is the largest known star in the universe, and most of what fills that enormous volume is absence. That is not a diminishment. That is what makes it remarkable. The universe built the largest known stellar object, not from extraordinary density, but from extraordinary diffusion, from a process that took an enormous mass and spread it to its absolute physical limit, right to the edge of the Hayashi boundary, where any further expansion would make the outer layers too loosely bound to remain part of the star at all. And at that edge, something is already happening. The outer layers are not perfectly still. They are not fully bound. They are leaving. The outer atmosphere of Stephenson 2-18, diffuse, cool, loosely gravitationally bound, pulsating over timescales of years, is already in the early stages of being lost. Not catastrophically, not all at once, but continuously, steadily driven by a combination of the star's own radiation pressure pushing outward on the material above it, and pulsation shocks moving through the atmosphere like slow waves through a fog, carrying mass to escape velocity and releasing it into the space between stars. Every year, Stephenson 218 is losing material equivalent to a measurable fraction of the Sun's total mass. Gas and dust streaming away from it into the surrounding interstellar medium, building up in layers around the star, creating circumstellar shells, rings of ejected material that surround the star, like the faint expanding aftermath of a long, slow exhalation. The star is coming apart, slowly, inexorably, and long before its core delivers the final catastrophic event that ends everything. The star is already shedding the body it spent millions of years building. The dying has already begun, not in the future, not when the core finally fails. Right now, at this moment, as we observe it from 20,000 light-years away, Stephenson 218 is shedding its own body into space, continuously, irreversibly. The largest known star in the universe is coming apart. A structure does not have to shatter to be failing. A dam does not need to burst to be losing water. Sometimes the failure is quiet, a slow seep through hairline cracks, material moving outward grain by grain, the structure hollowing itself from within while its outer face still holds its shape. The failure is real, the loss is measurable, and by the time the collapse becomes visible, the damage has already been accumulating for centuries. Stephenson 2-18 is failing in exactly this way. The outer atmosphere we examined, diffuse, cool, loosely held, spread across a volume 10 billion times the Sun's, is not static. Gravity's grip on those outermost layers has been weakening for hundreds of thousands of years, and something has been pushing back against even that weakened grip, driving material away from the star and into the space surrounding it, not in a catastrophic burst, in a continuous, accelerating, unstoppable flow. Astronomers call it a stellar wind. The name understates what it actually is. A stellar wind is a flow of gas streaming continuously outward from a star's surface, driven by the pressure of the star's own radiation pushing against the material in its atmosphere. Radiation pressure, the physical force that light exerts on whatever it encounters, sounds almost negligibly small at everyday scales. Hold your hand in sunlight and you cannot feel it pushing against your palm. though it is technically doing so. But across the surface area of a star as vast as Stephenson 218, radiating energy at hundreds of thousands of times the Sun's luminosity, that same gentle pressure becomes a force capable of accelerating gas to tens of kilometers per second and carrying it away from the star permanently. For our Sun, the solar wind is modest, a thin, fast stream of particles that reaches Earth and creates the auroras at our poles, but carries away only an extremely small fraction of the Sun's mass over its entire lifetime, negligible in stellar terms. For Stephenson 2-18, the situation is categorically different. A red supergiant at this luminosity, based on estimates for similar stars and the general physics of evolved massive stars, likely loses somewhere between 100 millionth and 1/10,000th of a solar mass every single year to its stellar wind. 1/10,000th of a solar mass per year. That translates to roughly 30,000 Earth masses of material lost every year. Every year, year after year, decade after decade, without interruption. 30,000 Earths gone, drifting away into interstellar space, carrying with them the material that once formed the star's outer body. Hydrogen, helium, the molecular compounds that formed in the cool outer layers, the titanium oxide, the water vapor, all of it streaming outward at roughly 10 to 35 kilometers per second, or about 6 to 22 miles per second. But the wind alone does not tell the full story, because something happens to that escaping gas as it moves away from the star, something that makes the mass loss self-reinforcing, a feedback loop that accelerates its own process. As the gas moves outward from the photosphere, it cools rapidly. The star's surface sits at roughly 3,200 degrees, cool enough, as we established, for molecules to form. But a few stellar radii above the surface, the temperature drops further still, and at temperatures below roughly 1,500 degrees, something remarkable happens to the material in the outflowing wind. The gas begins to condense, not into liquid, not into ice, into tiny solid grains, microscopic particles of silicate, of carbon, of aluminium oxide, dust, the same class of material that formed the interstellar dust clouds that once obscured Stephenson 218 from our instruments is now being manufactured in the star's own outflowing wind. Think of steam rising from a cup of hot liquid. As that steam moves upward into cooler air, it condenses, droplets form, then water. The principle is the same in the stellar wind, scaled to temperatures and distances that have no equivalent in any kitchen. The gas cools, chemistry happens, and tiny solid grains appear. And here is where the feedback begins. Those dust grains are extraordinarily good at absorbing radiation, far better than the gas alone. The star's light pressure acts far more forcefully on dust than on gas. The moment dust forms in the outflowing wind, radiation pressure grabs it and accelerates it outward with renewed force. The dust drags the surrounding gas along with it. The mass loss rate climbs, more material escapes, more dust forms. The wind strengthens. The star is, in a real sense, helping to dismantle itself. But the wind and the dust are not the only mechanisms at work. The pulsation, the years-long breathing rhythm of the outer atmosphere we examined in the previous chapter, adds its own contribution to the mass loss. Each pulsation cycle generates pressure waves. Think of them as slow, enormous sound waves moving outward through the star's diffuse atmosphere, carrying energy from the interior toward the surface. When those waves encounter the density gradient at the outer atmosphere, they steepen into shocks. A shock wave is a pressure front moving faster than the speed of sound in the surrounding material, a sudden, sharp compression followed by an equally sudden rarefaction, like the crack of a breaking branch amplified to planetary scale. Those shocks lift material. Physically, mechanically, they accelerate parcels of gas upward, beyond the escape velocity of the star's weakened gravitational field. Not all of the material lifted by each shock escapes. Some falls back, rejoins the atmosphere, but some does not. Some crosses the threshold, and every pulsation cycle, that threshold is crossed again and more material departs. The combination, radiation-driven wind, dust-enhanced pressure, pulsation shocks, creates a mass loss rate that no stable stellar configuration can sustain indefinitely. We have seen this process in action on a star close enough for our instruments to document directly. In late 2019 and early 2020, the red supergiant Betelgeuse, a star roughly 700 light-years away, familiar as the bright reddish star at the shoulder of the constellation Orion, dimmed dramatically. Not slightly. By late 2019, it had faded to roughly 40% of its normal brightness. Astronomers around the world turned their instruments toward it, uncertain of what they were seeing. Subsequent observations by the Hubble Space Telescope, published in 2022, revealed what had happened. A convulsion in Betelgeuse's outer layers had ejected an enormous mass of hot gas, equivalent to several times the mass of the Moon, into the space surrounding the star. That gas cooled as it moved outward, forming a cloud of dust that briefly obscured part of the star's surface from our line of sight. Not a supernova, not a collapse, a mass ejection, one episode, lasting months, in the ongoing process of a red supergiant shedding its outer body. Betelgeuse is significantly smaller than Stephenson 218. Its mass loss rate is considerably lower. If Betelgeuse can eject that much material in a single convulsive event, the implications for a star at the scale and luminosity of Stephenson 218, with its far stronger radiation pressure, its more extreme pulsation, its outer layers held by weaker gravity, are considerable. You are standing in the circumstellar shell, the region of space surrounding Stephenson 218, where the ejected material has been accumulating for hundreds of thousands of years. In every direction, moving slowly outward around you, the remnants of the star's own body, gas that was once the star's atmosphere, dust grains smaller than a wavelength of visible light, formed from the star's own chemistry, condensed from its wind. The material is too sparse to see. Passing through it, you would feel nothing, just as you would feel nothing moving through the star's outer atmosphere itself. But your infrared instruments would register it immediately, glowing faintly with the residual warmth of its long journey outward, building up in layers like the rings of a very slow, very patient tree, each layer representing another few thousand years of continuous loss. The outermost shells in structures like this extend, in some observed red supergiants, to distances of several light-years from the star. A light-year being the distance light travels in a year, roughly 9.5 trillion kilometers, or about 6 trillion miles. The star's shed skin, drifting in rings through the surrounding interstellar medium, marking the history of its slow dissolution in concentric circles of cooling dust and gas. This is the biography of a star writing itself in matter, in the space around its own body before it dies. Dust forming from nothing, microscopic grains of silicate condensing from cooling gas, invisible to any human eye, drifting outward through the interstellar dark, carrying the chemistry of a dying star toward wherever the next cloud will collapse and the next world will form. What all of this amounts to, the wind, the dust feedback, the pulsation shocks, the circumstellar shells, is a star in what astrophysicists recognize as its terminal phase, not approaching instability, in instability. The mass loss is not a minor perturbation around a stable equilibrium. For a star at the luminosity and radius of Stephenson 2-18, it is the dominant process of its current existence. The star is defined, right now, more by what it is losing than by what it retains. 100,000 years ago, when Homo sapiens had not yet begun the migrations that would carry our species across the planet, the progenitor of Stephenson 218's current red supergiant phase had likely already begun its mass loss. Over that time, that span encompassing the entirety of human prehistory, the rise and fall of every civilization, every language ever spoken, every war ever fought, The star has been continuously bleeding material into the space around it. Several solar masses, based on estimates for stars of this type, may have already been lost. Material that was once part of the largest known star now drifts silently through the Scutum-Centaurus arm, cooling, dispersing, eventually becoming part of the next molecular cloud that collapses into the next generation of stars. We cannot know, from 20,000 light-years away, exactly how much of its mass remains. We cannot know where in its terminal evolution the star currently sits. The light we receive tonight left the star 20,000 years ago, before the last ice age ended on Earth, before the first cities were built, before writing was invented. The star we are observing in our instruments is a historical document. Its present state is unknown to us, and may remain unknown for as long as humans have existed. That is not a failure of science. That is the honest condition of observational astronomy across cosmological distances. But here is what makes the mass loss not merely a story of ending. The material leaving Stephenson 2-18 is not disappearing. The dust forming in its wind, silicate grains, carbon particles, is the same class of material that eventually forms the solid cores of new planets. The gas streaming outward carries hydrogen and helium, and heavier elements synthesized in the star's own interior, enriching the interstellar medium with chemistry that was not there before. The circumstellar shells, drifting outward over millions of years, will eventually merge with the broader interstellar medium, contribute to new molecular clouds, and seed the raw material for the next generation of stellar and planetary formation. Every solar mass that Stephenson 2-18 loses is not a loss to the universe. It is a contribution, a deposit. The star is already, in its slow dissolution, beginning the process that will eventually become something else, something we cannot name, in a time we cannot reach. What is falling apart is also, from a longer perspective, being given away. The outer layers are thinning, the circumstellar shells are thickening. The star is smaller today, probably, than when the light we observe left it, but the core, sealed beneath all of that, has continued its own parallel story. Contracting, heating, building through layers of nuclear burning, helium, carbon, neon, oxygen, silicon, each one igniting as the previous fuel runs out, each one burning faster than the last, each one buying the star a shorter and shorter reprieve, until, at the very end of that sequence, the core reaches a threshold that nothing in the universe can reverse. The creation of iron. Iron is where fusion stops generating energy. Iron is where the core's ability to push back against gravity collapses in under a second. And what follows that collapse is not a continuation of the slow, quiet dissolution we have been describing. What follows takes the energy output of 100 billion stars and releases it in the span of a few minutes. The slow death we have been watching is nearly over. What replaces it is not slow, and it is not quiet. In under 1 second, everything changes. The core of a massive star, a sphere of iron roughly the size of Earth containing more mass than the Sun, collapses to a ball 20 kilometers across. 20 kilometers. The entire energy released in that moment exceeds everything the Sun will produce across its entire 10 billion year life. And it all happens before a human being could finish a single heartbeat. The slow dissolution we have been describing, the stellar winds, the mass loss, the quiet diffusion of the outer atmosphere over hundreds of thousands of years, gives an impression of a star winding down gradually, fading, thinning into nothing the way a fire dies when it runs out of wood. A long, quiet ending. That impression is wrong. The ending of a star like Stephenson 2-18 is not quiet, and it is not slow. The slow dissolution is the preface. What terminates it is something of a different category entirely, an event so sudden, so energetic, and so physically extreme that describing it requires borrowing the vocabulary of the most powerful phenomena the universe produces. Before we get there, we need to understand what the core has been doing while the outer layers were drifting away. From the moment the progenitor star exhausted its core hydrogen millions of years ago, The core has been on a predetermined sequence. Hydrogen burning gave way to helium burning. Helium gave way to carbon. Carbon to neon. Neon to oxygen. Oxygen to silicon. Each fuel igniting when the previous fuel ran out. Each successive stage running faster than the last. Each one generating less energy per unit of fuel consumed. Think of it as a relay race where each runner is slower than the one before, and each leg of the race is shorter. The hydrogen burning phase lasted millions of years. The silicon burning phase, the last stage, where silicon nuclei are fused into iron, lasts roughly 1 day. 1 day. After millions of years of burning, the final fuel stage runs for approximately 24 hours, and then the iron forms. Iron is where fusion stops generating energy. Every element up to iron in the periodic table releases energy when fused. The nuclear reactions that power every star, that warm every planet with a parent sun, that built every element in the chemistry of life, all run on the principle that combining lighter nuclei into heavier ones releases energy up to iron. Iron is the bottom of the energy valley. Fusing iron absorbs energy rather than releasing it. For a stellar core, iron is not just a product, it is a dead end. As the silicon burning produces iron, the iron accumulates, a growing sphere of inert, energy-neutral material building at the center of the star. No outward pressure to counteract gravity, no fusion reactions pushing back, just mass, accumulating, pressing inward on itself under gravity that has been pulling since the star first formed. The iron core can support itself, up to a point. The quantum, mechanical pressure of electrons packed tightly together provides some resistance, but that resistance has a limit. When the iron core reaches approximately 1 4/10 times the mass of our Sun, a threshold identified by the physicist Subrahmanyan Chandrasekhar in the 1930s. The electron pressure fails. The limit is crossed. Imagine a building whose internal support structure has been quietly, invisibly failing for years. Hairline fractures spreading through the load-bearing walls, the foundations softening imperceptibly, the whole structure held up by increasingly thin margins of structural integrity. From the outside, nothing looks wrong. The building stands. And then, in the instant the last threshold is crossed, it doesn't. Not slowly, not floor by floor. All at once. The iron core of a massive star collapses in exactly this way, and the timescale makes the building analogy feel generous. The inner core, a sphere roughly the size of Earth, collapses to a ball approximately 20 kilometers across, or 12 miles, in less than 1 second. Less than the time it takes to draw a single breath. A volume of space containing more mass than the Sun compresses to the size of a small city in under a second, reaching densities so extreme that individual protons and electrons merge into neutrons, and the matter produced is unlike anything in ordinary physical experience. A neutron star, a sphere of essentially pure nuclear matter, spinning and radiating at the very edge of what matter can be, before collapsing further into a black hole. At the center of what was once the largest known star in the universe, a city-sized ball of neutrons appears, almost instantly, and the outer core, still falling inward, strikes that newly formed surface. The collision of the outer core with the newly formed neutron star generates a shock wave, an outward-moving pressure front of extraordinary violence traveling at tens of thousands of kilometers per second. At that speed, it would cross the entire diameter of Earth in less than half a second. In minutes, it propagates outward through the star's interior, pushing through layers of oxygen, neon, carbon, and helium that have been sitting undisturbed for millions of years. But here is where the physics produces one of its most unexpected twists. The shock stalls. The outward-moving pressure front, powerful as it is, loses energy as it moves through the dense stellar material. Within roughly a second of its formation, it has slowed, weakened, and risks dying out before it can eject the stellar envelope entirely. On its own, the shock is not enough. What saves it, What revives the stalled shock and drives the explosion outward is neutrinos. Neutrinos are subatomic particles so weakly interacting with ordinary matter that they pass through virtually everything without resistance. Right now, roughly 65 billion neutrinos from our Sun pass through every square centimetre of your skin every second, through your body, through the floor beneath you, through the planet itself, without stopping or deflecting. They are the most ghost-like particles physics knows. But in the dense environment immediately surrounding a collapsing stellar core, the density is so extreme that even neutrinos, for a brief moment, interact with the surrounding material. The collapsing core produces an extraordinary burst of neutrinos, carrying approximately 99% of the entire energy of the supernova explosion. That is not a rounding error. Of all the energy released when a massive star dies, only 1% goes into the visible light, the shock wave, the ejected material. 99% departs as neutrinos that pass through the explosion and continue outward at nearly the speed of light, through the star, through the surrounding shells, and into interstellar space. But that 1% of deposited neutrino energy, deposited in the brief, extraordinarily dense moment when even neutrinos interact, is enough to revive the shock, enough to push it outward through the remaining stellar layers, enough to eject the envelope. The explosion begins. We have watched this happen, not to Stephenson 2-18, to a different star, a blue supergiant in the large Magellanic Cloud, a small companion galaxy to our own Milky Way, roughly 160,000 light-years away. On February 23, 1987, the neutrino detectors at Kamiokande 2 in Japan, and at the Irvine, Michigan Brookhaven facility in the United States, and at the Baksan Underground Scintillation Telescope in the Soviet Union, all registered an anomalous burst of neutrino detections within a window of roughly 12 seconds, 23 neutrinos, detected from a stellar collapse 160,000 light-years away, a vanishingly small fraction of the flood that had passed through, but enough. The instruments recorded that a stellar core collapsed. Roughly 3 hours later, visible light from the supernova, designated SN 1987A, arrived at Earth. Telescopes in the southern hemisphere captured it brightening over the following days, reaching a peak visible to the naked eye. Astronomers around the world turned every available instrument toward it. The neutrino burst had arrived first. The death announcement, sent in particles we cannot see, arrived 3 hours before the light we could. For Stephenson 2-18, 20,000 light-years away rather than 160,000, the neutrino burst would arrive proportionally earlier relative to the light, and the energy released from a star orders of magnitude more luminous than the progenitor of SN 1987A would be correspondingly greater. Right now, as you sit reading this, roughly 65 billion neutrinos from our Sun pass through every square centimetre of your skin each second. You feel nothing. They have been passing through your body every second of your entire life, and you have never once detected them. When Stephenson 2-18 dies, whenever that moment comes, whatever it looked like 20,000 years ago on the other side of the galaxy, a neutrino burst will arrive at Earth. In the minutes before the visible light of the explosion reaches our telescopes, those neutrinos will pass through everything, through the atmosphere, through every building on the surface of the planet, through every human body alive at that moment, through the ocean floor, through the planet's iron core, and out the other side, all of them undetected by human biology, gone, and then the light will arrive. The total energy released in a core collapse supernova is approximately 10 to the 44th power joules. That number means nothing stated alone, so consider this. Our Sun, over its entire 10 billion year lifespan, burning steadily from the moment it ignited to the moment it eventually dies, will radiate a total energy strikingly close to that same value. The supernova releases in a matter of seconds an amount of energy comparable to everything our Sun will ever produce across its entire existence. In seconds. At peak brightness, a core collapse supernova outshines the combined light of every star in its host galaxy, all 100 billion stars or more, all burning simultaneously for days to weeks. From 20,000 light-years away, Stephenson 218's eventual supernova would appear in Earth's sky as a new object, likely visible during daylight for a period of time, fading over weeks and months as the ejected material expands and cools. The light would carry information about the explosion for years after the event itself. Historical records exist of supernovae observed by naked-eye astronomers before modern telescopes. The guest star of 1054 AD, recorded by Chinese and Arab astronomers, produced the Crab Nebula, visible today as an expanding cloud of gas, nearly 7,000 light-years away. At its peak, accounts suggest it was visible in daylight, a star dying, announcing itself in light, recorded by humans who had no framework to understand what they were seeing. Stephenson 2-18 will do the same. At some point, perhaps already, given the 20,000-year delay in the light's arrival, it has or will produce exactly this announcement. But the explosion is not merely destructive, it is generative in a way that has direct personal consequences for every person alive on Earth today. The supernova shockwave, moving outward through the stellar layers, drives nuclear reactions that produce elements heavier than iron, elements that could not be forged by the fusion processes that powered the star during its life. In the extreme temperatures and neutron fluxes generated by the shock and the neutrino burst, rapid neutron capture, the R process, builds nuclei by stacking neutrons onto existing atomic structures faster than radioactive decay can disassemble them. The R process, the rapid neutron capture process, is the mechanism by which the universe produces gold, platinum, silver, uranium, thorium, and dozens of other heavy elements. These elements exist in the crust of the Earth, in the oceans, in the human body in trace amounts, because supernovae like the one Stephenson 2-18 will eventually produce manufactured them in the seconds of the explosion and scattered them into the interstellar medium. The gold in any ring on any hand anywhere on Earth was forged, almost certainly, in the core collapse supernova of a massive star that died before our sun was born, the uranium in nuclear reactors, the iodine in a human thyroid, the platinum in a catalytic converter, all of it produced in the brief, violent, generative moment when a stellar core collapses and a shockwave tears through the layers of a dying giant. Stephenson 2-18, when it dies, will contribute to that inventory. The elements forged in its explosion will disperse across the Scutum-Centaurus arm, enrich the molecular clouds that follow, and eventually find their way into the chemistry of whatever comes next. Stars, planets, and perhaps in some unimaginably distant future, into the bodies of things that wonder where they came from. Gold, heavier than almost anything the Earth's crust produces naturally. Dense, warm to the touch, glinting in ordinary light, every atom of it forged in the seconds of a stellar death, scattered across light years of space, accumulated over billions of years into the ground beneath our feet. When the explosion fades, something remains at the center, either a neutron star, a city-sized sphere of nuclear matter spinning hundreds of times per second, generating lighthouse beams of radio radiation that sweep across space with metronomic precision, or a black hole, a region where the collapsed remnant exceeded even the neutron pressure limit and gravity won completely, creating a boundary from which nothing, not even light, can escape. For a star of Stephenson 2-18's estimated progenitor mass, 25 to 40 solar masses, already reduced by millions of years of stellar wind mass loss, the outcome is genuinely uncertain. Some models suggest that very massive stars collapse directly to black holes without producing a visible supernova at all. Others suggest a full neutrino-driven explosion followed by a neutron star. The observational record includes cases of both. We do not currently know which outcome awaits Stephenson 2-18 specifically. What we do know is that the outer layers, the vast, diffuse atmosphere that once stretched across 2,000 solar radii, that contained water vapor and titanium oxide molecules that pulsated over years and shed material for hundreds of thousands of years, will be ejected into the surrounding space at a significant fraction of the speed of light. That material, enriched with the elements of the explosion, will expand for thousands of years, forming a nebula, a glowing, expanding cloud of gas and dust that will eventually merge with the interstellar medium and seed the next generation of stars. The star that was built from a collapsed molecular cloud will at its end become the cloud that builds what follows. The explosion is complete. The heavy elements are dispersed. The remnant, neutron star or black hole, sits at the center of an expanding nebula, cooling, quieting, becoming just another object in the catalogue of extreme astrophysical phenomena that fill the galaxy. And from 20,000 light-years away, long after all of this has happened, the light of it all is still travelling toward us. But before we arrive at what all of this means for Stephenson 218, for the galaxy, for the atoms in our bodies, and the question of why any of us are here at all, there is one more question worth sitting with. What does it mean that we found this star? What does it mean that human beings on a small planet built instruments that could penetrate 20,000 light-years of dust, decode the chemistry of a star's atmosphere from its light, and arrive at a number, 2,150 solar radii, that defines the current known limit of stellar size? What does the largest known star mean? Not as a data point, not as a record, but as a fact about the universe we inhabit, and about what kind of creatures we are to have noticed it at all. Everything we have covered, the dust wall, the cluster, the size that swallowed solar systems, the measurement built from inference, the star slowly coming apart, the death that forges gold, all of it converges here, not into a conclusion, into a question about what any of it means for the person who has been listening. Records in science tend to feel stable, the largest, the fastest, the most massive. We treat them like fixed facts, entries in a catalogue that define the edges of the known, and there is something genuinely satisfying about that. To know where the boundary is, to be able to say, this is the largest star we have found. But Stephenson 2-18 is not simply a record, and this story was never simply about size. The size was the door. What was behind it, the physics of how a star becomes this large, the paradox of enormous volume and near emptiness, the molecular chemistry forming inside a stellar atmosphere, the slow dissolution of a body held together by forces that have been weakening for millions of years, the death that releases energy equivalent to a sun's entire lifetime in seconds, the elements forged in that death that are right now inside you. That is the story. And to understand it fully, we need to sit with what it means that we found it at all. The red supergiant phase of a star like Stephenson 2-18 lasts, based on current stellar evolution models, somewhere in the range of a few 100,000 years. A few 100,000 years against the 4.5 billion year history of Earth. That phase represents less than 0.1% of a single planetary lifetime. It is a window, narrow, specific, already closing. We are watching it through that window right now. The light arriving in our infrared instruments from the Stephenson 2 cluster left that region of space roughly 20,000 years ago, before the last ice age ended, before the first cities were built, before any written record of human experience existed. That light crossing the dust-obscured Scutum-Centaurus arm for 20,000 years carries the image of a star in a phase of its existence that will not last. In a few 100,000 years, a blink on cosmic timescales, Stephenson 2-18 will either have exploded or further evolved beyond what it is today. The object we have been describing will be gone. Future astronomers, if there are any, wherever they are, in whatever form intelligence takes 10 million years from now, will not see Stephenson 2-18 as a red supergiant. They will see its remnant, if they can find it at all. The extraordinary, record-breaking, physically paradoxical object we have spent this entire journey examining as a temporary phenomenon, specific to this moment in cosmic history. We happen to exist in that moment. We happen to have built instruments capable of seeing through the dust that hid it for all of human history. And we happen to have done so while it is still there to see. That is not nothing. That is a privilege that belongs specifically to this generation of observers, on this planet, at this point in cosmic time. But here is the honest uncertainty that any serious account of Stephenson 218 must carry. We do not know if it is truly the largest star in the universe. We do not even know if it is the largest star in the Milky Way. The Milky Way contains somewhere between 100 and 400 billion stars. Of those, the fraction that are currently in the red supergiant phase, that brief, extreme, record-eligible window, is estimated at perhaps a few thousand objects galaxy-wide, a few thousand out of hundreds of billions, and of those, an unknown number are hidden behind dust walls like the one that concealed Stephenson 218 for all of human history. Infrared astronomy cracked that first wall open, but it has not penetrated every wall. In the densest regions of the galactic plane, even infrared surveys are attenuated and incomplete. Stars larger than Stephenson 218 could exist right now, in the Scutum-Centaurus arm, in the Norma arm, in the dense stellar nurseries near the galactic center, and our current instruments would not have found them yet. Science does not have the answer to the question of whether Stephenson 2-18 is the true maximum. It is the current known maximum. The distinction matters. It means the catalogue is still open. It means the next generation of infrared surveys, the next space observatory with improved dust-penetrating capability, the next careful analysis of an overlooked data set could move the boundary further, could find something larger. The record is real. The record is also provisional, and the universe has a long history of exceeding what we believed were its limits. What Stephenson 2-18 does represent, regardless of whether larger stars eventually emerge from behind dust, is the observable boundary of stellar physics as we currently understand it. A star cannot expand indefinitely. The Hayashi limit, the maximum radius permitted by the physics of convective energy transport in a stellar envelope, imposes a ceiling. Stephenson 218 sits near that ceiling. Based on what we know about stellar physics, a red supergiant of this luminosity at this evolutionary stage cannot be substantially larger without becoming gravitationally unbound, without the outer layers simply escaping into space faster than the star can maintain them as part of its own body. 2,150 solar radii is not merely a measurement. It is, within the range of current understanding, close to the maximum that nature's own rules permit. Finding Stephenson 218 is not just finding the largest known star, it is finding something very near to the largest possible star, a natural experiment at the absolute boundary of what stellar physics allows. That is a remarkable thing to have found. And the fact that it was hidden behind dust for all of human history, waiting to be revealed by a form of light our eyes cannot see, makes it more remarkable still. Hold up your hand. The calcium in the bones beneath your skin was forged in the core of a star. Not this star, but a star that lived and died before the sun was born, in a supernova that scattered its contents across the interstellar medium, which eventually collapsed into the molecular cloud that formed our solar system. The iron in the hemoglobin of the blood moving through your fingertips right now was forged in the collapse of a stellar core, the same catastrophic event we described in the previous chapter, the same physics that will eventually produce the remnant of Stephenson 218. The carbon in every cell of your body, the oxygen in your lungs, the nitrogen in the proteins that build your muscles. All of it emerged from stellar interiors more extreme than anything in our immediate solar neighborhood. You are made of the aftermath of stars like Stephenson 2-18, not metaphorically, not poetically, in the way people sometimes use that phrase as a kind of decorative flourish, chemically, physically, atom by atom. The largest known star in the universe is not a curiosity from a distant region of the galaxy. separated from your life by 20,000 light-years of space. The process it embodies, birth, burning, expansion, dissolution, death, dispersal, is the process that produced the matter your body is assembled from. You are not separate from this story. You are its most recent chapter. There is a pattern in what Stephenson 2-18 represents, one that runs through all of stellar evolution, but that becomes most visible at the extreme. The universe builds giants. It invests millions of years, vast quantities of mass, extraordinary physical processes in constructing objects of this scale, and then it erases them, not because the universe is wasteful, but because the erasure is the point. The death of Stephenson 2-18, the supernova, the heavy element synthesis, the expanding nebula dispersing into the interstellar medium, is not the end of the story. It is the mechanism by which the story continues. Every massive star that has ever died has enriched the galaxy with the chemistry needed for the next generation of stars, planets, and whatever forms on those planets. The giants are temporary. The contribution is permanent. Our Sun, a second or third generation star, formed partly from the debris of earlier stellar deaths. Earth formed from the same debris, enriched over billions of years by supernova after supernova. The chemistry that allowed life to arise here, carbon, oxygen, nitrogen, phosphorus, iron, was deposited into the molecular cloud that became our solar system by stars that lived and died long before we existed. Stars of the same class, the same extreme category as Stephenson 2-18. We exist in the aftermath of ancient stellar deaths. That is not a poetic observation. That is the accurate physical description of our origin. The night sky above you right now, every visible point of light a star in some phase of the same process, burning, building, eventually dissolving into the interstellar medium, giving back what it was given, making the next thing possible. We have travelled a long distance together in this story, from a modest infrared survey catalogue entry in 1990 to the physical limit of what a star can be, from the dust that hid Stephenson 2-18 to the measurements that revealed it, from the solar system it would swallow to the atoms in your body that came from stars just like it. That distance from discovery to meaning is what science actually is. Not a collection of facts, a continuous journey of asking what something means, following the answer into deeper questions, and arriving somewhere we did not expect when we began. You came here tonight with a question about the largest star. You leave with something larger than that. In 1990, an infrared survey cracked open a door that visible light could never have opened. The wavelengths that pass through the dust, the ones our eyes cannot register, the ones that carry heat rather than visible colour, were the only path to Stephenson 2-18. Without light we cannot see, the largest known star would remain unknown, hidden, irrelevant to our catalogue of the universe. But that same invisible light, infrared radiation, the warmth emitted by objects too cool or too distant for our eyes, connects us to Stephenson 2-18 in a way that goes deeper than instrument readings. The energy flowing outward from every stellar interior, carrying heat toward the surfaces that eventually explode and scatter heavy elements into space, is the same class of radiation. The photons that carried the news of this star's existence to our telescopes are cousins of the photons that carried energy outward from the stellar cores that forged our atoms. The light we cannot see revealed the star. That made us possible. That is the full meaning of the motif. Not a clever bookend, a genuine physical truth. The invisible is not separate from our world. It is the infrastructure our world was built on. Stephenson 2-18 stands at present at approximately 2,150 solar radii. Based on current estimates, it represents the closest known approach to the physical ceiling that stellar physics allows. It burns at 3,000 degrees. It pulsates over years. It sheds its outer layers into space in continuous, irreversible dissolution. It carries water vapor in its atmosphere. And it will, at some point, either already has or will, collapse in under a second, generate a burst of neutrinos carrying 99% of its death energy through everything in the galaxy without stopping, forge heavy elements in the violence of the explosion, and leave behind either a spinning neutron star or a black hole at the center of an expanding nebula. All of that, from the first infrared photon that reached Stephenson's survey detector to the gold that will eventually be scattered through the Scutum-Centaurus arm by the supernova, represents the full cycle of what the universe does with its most extreme constructions. It builds them to give them away. The largest known star is not a monument, not a permanent fixture of the cosmos. It is a process, a particular phase of a transformation that began millions of years ago and will continue long after the star itself has ceased to exist. The size we measured is a moment in that process. The meaning is in the entire arc. We are the universe looking back at itself, not in any mystical sense, in the most literal one available. The atoms that form the neurons reading these words were forged in stellar cores and scattered by stellar deaths. The curiosity that drove a team of astronomers to point an infrared survey at a dust-obscured region of the galaxy and notice an extraordinary concentration of red supergiants, that curiosity is itself the product of the same stellar chemistry. The fact that one of those supergiants turned out to be the largest known star in the universe, hiding behind light we could not see for all of human history, and that we now know it, that is the universe having generated, through billions of years of stellar birth and death and dispersal, something capable of noticing the process that generated it. Stephenson 2-18 will not notice us. The universe does not notice anything. It simply continues, building and erasing, forging and dispersing, indifferent to scale, indifferent to record books. The noticing belongs to us. And the noticing, the act of looking through the dust, decoding the light, calculating the radius, walking through the solar system in thought, sitting with the paradox of a star mostly made of emptiness, following the chain from molecular cloud to dust grain to gold atom to human body. That act is what makes the scale meaningful, not to the universe, to us. We are not separate observers of something happening far away. We are participants in the same process, built from the same materials, illuminated by the same physics, separated from Stephenson 2-18 by distance but not by origin. The largest known star is not out there. In the most important sense, it is also in here. Tonight, you learned about something enormous, but what stays with you, if anything stays, probably won't be the size. Not the 2,000 solar radii, not the solar systems it would swallow, not the energy of a collapsing core released in seconds. What stays will be quieter than that. The strange, soft recognition that the universe has been doing all of this, burning, collapsing, forging, scattering, building again, for billions of years before any living thing existed to notice, that all of it happened in complete silence, complete darkness, with nothing present to call it remarkable. And then, after an almost incomprehensible amount of time, something appeared that could. You appeared. Not because the universe was building toward you, not because any of this had a direction or a purpose or a destination, but because the same physics that inflates a star to 2,000 solar radii also, given enough time and the right conditions, produces a person sitting quietly in a room at night, feeling something they cannot quite name. That feeling, right now, whatever it is the rarest thing the universe has ever made. Not the giant, the one who noticed it,